Now recording. Okay, forgot to do that. Sorry about that. For those who just came in and those who are just coming into the thing, I left off the first part. You'll have to look at the recording from last week when we went through Blackboard and the syllabus, but that's where you find it. So let me go back to this. All right. All right. We were looking at the weekly assignments, and there's week 1. Open that one. Well, again, it's so incredibly slow. There it opened. This is where we were, instructional materials. It's very slow, but it's opening. All right, and there was the recorded lectures. There's the PowerPoints for Chapter 5. Here is the recorded lectures, a YouTube playlist for recorded classes. Now, I recorded last week. I'll be recording this week. Okay, let me show you what this looks like when you click on it. It takes you right to YouTube, right to the playlist. Now, I'm going to try to move this out of the way, but it's incredibly slow. All day long today it's been slow. I've tried to print things. They have taken forever. I don't know what's wrong with the system today. I think it's just this computer. This is a loaner from the college, but it's never been this slow before. And it's having trouble getting YouTube to open, but it will open in a few minutes, I think. There it goes. These at the top are the ones that I recorded in past terms, okay? And you'll see they cover all kinds of sections here. Some seem out of order. The ones down here, and you can't see it because this thing's in the way, or you can probably see it, I can't. Okay, you see down here PHY112 syllabus. That was last Wednesday's class. Okay, and what we're doing tonight will be beginning with section 5 or chapter 5, and when we finish recording it will probably replace this one here. Okay, so that's what happens. I'll record it, it'll go at the bottom, and I'll take this one off. So basically the whole course is on here. There may be a few gaps here and there, but basically the entire course is here. But this is how I taught it before. No guarantee this is how Dr. McBool will be teaching it. So anyway, I wanted to show you that. So I'm going to get out of YouTube now. Oh, here's Christevia. It's Christevia. Okay, this playlist, unless he takes it out, will remain on here. Okay, let me get Chris. Not. Oh, you mean on whatever they call it, Collaborate? No, I use Zoom. Now, maybe when Dr. McBool gets here, he'll use Collaborate. It's completely up to him. I use Zoom because people who had used both told me Zoom is better. Now, I don't know. That may be just their opinion, but my wife had Zoom, so I use it. She's married money, so she's rich. She can pay for it. It's not expensive. It's only like $15 a month or something like that, and we use it for family things and all sorts of things. Okay, so I'm going to, what's that? Okay, this is let me, yuck. Okay, I'm trying to, okay, now I'm trying to find, I seem to have lost the PowerPoint. So, I mean, not PowerPoint, Blackboard. So I'm going to try to get it back here. Right. And you were here last week, weren't you? Or not? I think you were. Okay. For some reason, it kicked me completely out of Blackboard. Yeah. So you heard basically everything we did this time. That's where we were. And for some reason, Blackboard got out. Blackboard is not, in my opinion, a very good package. It just, for some reason, booted out, and now I'm having to get back in. So bear with me a few minutes. Like I said, everything has been incredibly slow all day today with this computer. I don't know what's wrong with it, but it seems to be still on Christmas vacation or something. I don't know. You probably can't see it. Blackboard is sitting here, a little purple circle is just going around and round and round and nothing coming up. But this is how the whole day has been. I had a collaborate meeting with another instructor. It took us forever to get collaborate to open. I sat and watched it do this. That's when I was saying, oh, I'm so glad I use Zoom. And now Blackboard's doing the same thing. I don't think it's Zoom's fault. I think it's Blackboard's fault. But one of these days it'll quit doing this. Earlier I was getting so frustrated with it, I thought I was doing something wrong, but I found out if I just sit here long enough, it'll finally open. A student from the last term sent me some makeup tests and things like this, and I would find the test, go to open it, it would sit and do this. Then I go to print it, it would sit and do this. It was all Blackboard. Okay, and then when it finally went to the printer, it took forever for it to print. So the entire system has just been incredibly, incredibly slow. I mean, we're going to get to class in a few minutes, but it's taking a while. I guess I should just write your name down and fill it in later. I think I'll probably do that. Remind me, is it Christivia or Christavia? Okay, I thought so. On the thing, it looked like it was misspelled. Okay, and the last name was, you're probably the only Chris. It's what? Okay, there it just came back. Okay, I knew if I started doing that, it would go. And it always takes me back to Math 238, and there's absolutely no reason for it to do so. Then it takes me to this stupid thing called stream, which doesn't make any sense either. And then I get to go and find the course. And here it is. And now things have picked up a little bit. Okay, attendance. There we go. No one is enrolled in the course, it said. Okay. Jasmine Davis, still not here, right? And there's Christavia Dozier. They got your name spelled correctly here. Okay. So we're just missing Jasmine Davis and Chelsea Johnson. So that should mean that we have 18 present. Let me pull up the Zoom meeting again. And we have 18 present. Good deal, folks. Okay. Now, I'm going to go back to Google. No, I mean, not Google, Blackboard. And I'm sorry, this is, all right. What I had originally intended to show you, we haven't even gotten to yet. Okay. We went to weekly activities, and we looked at week 1, and that's where the link to the previous classes are. So they unless he removes them, they'll be there. Okay, I put them in for that reason, so you'll always have those. Week 2, I haven't done anything to because I kept thinking he was going to get approved this week. He hasn't. So I will go in and update this overview and weekly to-do list. Now this is a lot of this is Blackboard because Blackboard is just taking forever to open. You'll notice I don't have anything here. I'll try to get this updated in the morning. List the course objectives. Of course, it'll all be past tense then. It'll be stuff we did do, not what we would do. But in the future, hopefully he'll get these done ahead of time. I know I always did the day before or sometimes the week before. Instructional materials, I'll put in here again the PowerPoints, again, Chapter 5 PowerPoints. I'll just say, please see the YouTube playlist located in week 1. I won't put those again. I won't have any instructional videos, handouts, labs. We don't have any lab in this course or anything else. So it's pretty simple here. That's the part I'll show you. I will fill this out now that I'm teaching the course tonight. I didn't know I would be. So that's done. Let me now go to, are there any questions on anything while we're still here in Blackboard? Have the syllabus available? Anything else you want to see before we get started tonight? Okay, I hear nothing, so I'm going to go to PowerPoint. And if you remember, I don't speak very highly of this book. The book's good. The PowerPoint stinks, and the test bank stinks. I didn't like either one. The book is okay though. Okay, so let's go from current slide. Okay, I think we looked at this guy struggling last week, didn't we? We talked about what is a force. A force is a push or a pull. By the way, we're starting in Chapter 5. If you didn't pick up on that, we're in Chapter 5, and I think we're at the top of page 126. Do any of you have the books tonight? Or maybe I should say it this way. Do any of you not have the books tonight? I assume that some of you still do not. Is that right? No, the book is not a Cengage book. The book is a Pearson book. So it's not on Cengage Unlimited. But several people shared last time, and if you weren't here, go back in to that place on the YouTube video syllabus at the very bottom. Listen to that, and several people shared places where they rented the book. Okay, one was Amazon, the other was say again? Keg. Okay, so there's several places you can get it very, very reasonably. Now, for either of those, how long does it take to get here? Okay, and that's an ebook. How about Amazon? Was it Jasmine or whoever said that? 2 days to get there. So do you have your book already? Or is it an ebook? Oh, okay, good. All right. So you see, you can get books at pretty reasonable amounts. So is Amazon about the same as Chegg? Okay. And Jimmy, what did you say? 55. And where was yours? Amazon? Right. Okay. All right. So you can get it. And were y'all buying or were you renting? Rental. Okay. So renting the book, and you probably won't need the book after this term. So that's a pretty reasonable way to go. Okay. So this guy's still struggling with his pushing his box or crate or whatever it is. We're not anywhere close to the next slide. So from now on, if I can move y'all out of the way, Sharday, you're in the way again. No, I'm just kidding. Okay, I'm going to open the whiteboard again. And this is what I'll be using a lot because, okay, I'm going, on the whiteboard there is a taskbar, toolbar, something like that. They put right in the white space, so I moved it, and then I scoot the whiteboard over to the left and up as far as I can to give me maximum white space. There we go. All right. Now, we had just talked about, we had started section 5.2, which was on page 125, and force and the law of acceleration. And that was, we had earlier talked about Newton's first law, which was force and the law of inertia. The second law is, Newton's second law is, this book calls it the law of acceleration. I've seldom heard it called that, but that's what it is. F equal ma, where F is the total force acting on an object, m is the mass of that object, and a is the acceleration of that object. Okay. Now, here are a couple of things they write here, and since I don't, last time I typed because I didn't have my Wacom board set up then, but let me write now. One thing you'll note that force is proportional to the acceleration. The constant proportionality is the mass. So if the force goes up, the acceleration goes up. Or if something is accelerating, that must mean there's a positive net force acting on it. If it's decelerating, there's a negative net force acting on it. Okay? But mass is proportional to 1 over the acceleration. Because the larger the mass, the slower the acceleration. That makes sense. If you got a bowling ball, which is a lot more massive than a ping pong ball, the ping pong ball will accelerate much faster than a bowling ball. Okay, or let's say a golf ball and a bowling ball. Okay, now, what is the meaning? Now this book, instead of a proportional symbol like that, it uses the single crooked equality line. That's what they use instead of the proportional line. Most books in math and physics use this one. That's sort of like a fish symbol. I don't draw too well. The book uses that one. It doesn't really matter which one you use. So what is a force? Again, Newton's second law, force is equal to mass times acceleration. Okay, so if you have a 1 kilogram mass accelerating at 1 meter per second squared, that gives you a force of 1. Now you could write it out, kilogram meter per second squared. That's the basic units, kilogram meter per second squared. That is exactly the same as 1 Newton. Okay? A Newton is a unit of force named after good old Sir Isaac. That's why we capitalize it. Notice kilogram isn't capitalized, meter's not capitalized, second's not capitalized. Those aren't named after anybody. A Newton is named after someone, so we do capitalize the N in Newton. Okay? And that's how we define a Newton. It's 1 kilogram accelerating at 1 meter per second squared. Now, just a few things on units. Units are important. They're your friends. Keep up with them. An acceleration is always a distance divided by a time divided by a time again. This is, meter is your distance, second and second are your time, so it's 1 meter per second squared. That's sort of a shorthand. You could have written it 1 meter per second, but just to keep from having to write 2 slashes and 2 seconds, they write per second squared. If you ever have something that's meters per second, that's not an acceleration. That's a velocity. meters per second, or a speed possibly. Those have the same units. If it's just meter, that's a distance, okay? To be an acceleration, you need distance over time over time. In other words, distance over time squared. Oh, here comes Sydney, okay? Which I think she's already been here. I believe it's a she. Let me just check real quickly. Sorry about this, folks. There it is, document Google Chrome. Let me go back to, see, I should have a roll sheet, but I chose not to because I didn't think I'd be teaching the course. Okay, here we go. Attendance. Pretty sure I had her marked before. I thought so. Okay. No one's enrolled in your course. Okay. Just real quickly. I know you were. I remembered you were. Yeah, gotcha. Okay. All right. Let's go back to our, which were we on? The whiteboard, wasn't it? Okay. That's what a Newton is. It's a kilogram meter per second squared. A Newton is 1 kilogram meter. This pen sometimes works well and sometimes doesn't, per second squared. These are what I call fundamental units. And let me pause a moment here, time out again. The sort of 7 fundamental things you can measure. Mass is one. That's usually measured in kilograms, okay? Now, in a pure metric sense, that should be gram. But we use the SI system, which is System International. They use kilogram for the mass, okay? In the SI system, another fundamental unit is length. That's meter. Time, the fundamental unit is second, okay? Temperature, it would be Kelvin. We're not going to really do much with temperature, so you don't have to worry about that. If you were dealing with chemistry things, amount of a substance you have would be a mole. M-O is how they abbreviate that, or spell it out, M-O-L-E. We're not going to be messing with that. Intensity of light is a candela. We're not going to be messing with this. These are the 3 fundamental units we're largely going to be messing with. Mass, length, and time, and here they all show up in a Newton. Okay, a kilogram meter per second squared. Okay, now in the U.S. customary, this, by the way, is SI, standing for System International. French always put the, or quite often will put the noun first and the adjective after it. Rather, we would say international system, they say System International, so that's why it's SI. In the U.S. customary, that same equation, force equal mass times acceleration, in the U.S. customary system, mass is measured in, believe it or not, you probably have never heard of this unit before, a slug. How many of you have ever gone to the grocery store and said, I want a slug of potatoes? Okay. They would think you were nuts. They think you wanted a slimy little worm or something on it. That's not what it means. That's a unit. No one uses it except this book. No, I mean, really, in reality, they don't use it. Notice it doesn't even have an abbreviation. If you use it, you have to spell it out. Okay? Now, acceleration, remember I said, that's going to be a distance, and the fundamental unit of distance in the U.S. customary system is foot. Not meters, not yards, foot per second squared. And 1 slug foot per second square is 1 pound. Pound is not an equivalent measure to kilogram. Kilogram measures mass, pound measures force. Pounds and newtons are equivalent. They're not the same, but they measure the same thing. And a pound is 1 slug, no one ever uses that, foot per second squared. So don't worry about it. All you ever have to put is pound. This book is the only place that will ever have you trying to figure out how many slugs you have. No one really messes with those. Okay, we're finally down to example 1. Okay, so I'm going to clear the screen. Any questions before I clear the screen? Okay, whatever. Okay, clear the drawings. I thought I'd clear the drawings. I clear my drawings. Well, it's not. I hit the wrong button. Sorry. What force is necessary to produce an acceleration? Okay, now when I see a problem like this, I start writing down. What force? Other words, force is the thing we don't know. So I'm going to put a big question mark there. What force is necessary to produce an acceleration? So acceleration here is 6.00 meters per second squared. Okay, on a mass of 5.00 kilograms. Okay, there's your question. What force? Okay, now, what formula do we use? What is the basic formula for Newton's second law? F equal ma. Perfect. Okay, now all you do is plug and chug. But time out before we do that. Why in the world do they have 0.00 and 0.00 in there? Anyone having a clue why they put that in there? That indicates the precision of your measurement. And this, frankly, is totally unrealistic. I don't know of a single instrument, I'm sure there are some, but I sure don't have any, that will measure an acceleration to the nearest hundredth of a meter per second squared. That is a very precise device you have, and that you came out exactly 6.00. I could see 5.93, I could see 6.04, something like that, but to come out exactly 6.00, that's a mite. You're really, that's amazing. Same thing with mass. This is 5.00 kilograms. That means it's precise to the nearest hundredth of a kilogram. Okay, so basically what we say, both of those numbers have 3 significant digits. Okay, and if they have 3 significant digits, that means your answer needs how many significant digits? 3. No more, no less. Okay, well, what would that be then? Plug in your mass of 5.00 kilograms times 6.00. And by the way, I always slash my zeros. It's an old habit from the Navy. Okay, meters per second squared. And what does that give us? Anyone do that in your head? 30, not just 30, 30.0, 3 significant digits. Not 00, 3 significant digits, 1, 2, 3, there they are. Kilogram, meter per second squared. And what is a kilogram meter per second squared? Named after Sir, yes, A. Newton. That's a lot easier to write than kilogram meter per second squared. So 30.0 newtons. Perfect. Any questions on that? Pretty simple, huh? Okay. Ready for example 2. Since I took so much room there, I'm going to have to go to a clean page. Any questions before I erase it? There it goes. All right. Here's another one. What force is necessary? So again, we're looking for force. That's the unknown here. It's necessary to produce an acceleration. So the acceleration given is 2.00 feet per second squared. Okay, that alerts me we're in a different set of measurements. On a mass of 3.00, guess what? Slugs. No abbreviation for it. You have to spell it out. This is a very unrealistic problem. No one goes around measuring mass in slugs. It is the unit, but well, what is your force? Your force is, just like you said before, mass times acceleration, which in this case would be 3.00 slugs well, oh, and the answer, you put the same number of significant digits as you had in your problem and given in your problem. Okay, and we'll talk about later what if they're different numbers. We'll talk about that. You always go with the fewest number of significant digits. Like if this were 2.0 feet per second squared, but 3.00 slugs, 2 significant digits in acceleration, 3 in slugs, your answer would then just be 2. You can't have more precision coming out than what you put in. If any of you have ever done any computer programming, they used to have a phrase for that: garbage in, garbage out. Any of you ever hear that? Well, here it's precision in equals precision out. If you have 3 significant digits coming in all your units, then you do 3 coming out. And this one will look a little different, but it'll still be the same. Here is 2.00 feet per second squared. And this, someone do the math here, 6.00. You need 3 significant digits, so it's there. Remember, the last was 30.0 because every digit is significant. Don't do any other. Now, there will be times when some of these zeros are not significant, but these are, okay? Anything that follows a decimal point, any zero at the end of a decimal number is significant, okay? And this would be a slug foot per second squared. Now, my writing's pretty bad, but it's mostly this pen. Have any of you ever signed out of Home Depot or something with those ionizing pens? How close did that look like to your signature? Mine never does. This is a little better than those, but it's not a lot better. It's really jerky. It's not me being a jerk. Oh, McKendra is here. She was here already, wasn't she? I'm pretty sure she was. Okay, so she's back in now. So hopefully we'll be back up to 19. Well, I don't know. We must have lost somebody else. Okay, what is a slug foot per second squared? What's the other unit for that? Pounds. Perfect. And how they get LB, this must be some other language, but that's the symbol for pounds. All right, ready for example 3? Any questions on 2 before I leave it? Okay. Okay. Very good what you're saying here. And I'm not quite disagreeing with you. The number's not quite right. You're using, I think that's the conversion with grams and ounces, maybe. Newton is 2.2 pounds. But I'm sorry. You're right. Okay. You may be right. Yeah, a kilogram is 2.2 pounds. A Newton, yeah, that was your question. I was thinking the other. Okay. I'm glad you asked that, because if you go to the very back of your book, of course you don't have your books yet. At the very back of your book, there is an index. It covers a few pages there, 749 to something or another. And then for many pages in front of that, you have answers to odd number problems. Okay, some of them have all the answers, most of them are odds. Before that, and that started around 700 and I don't know, page 712 or so. Before that, you have an appendix E, which is basically a glossary. And that glossary begins at page 703. And before that, you have another appendix. And this appendix, let me read what it is scientific calculator. Not a bad place to go because we're going to be using scientific calculators a lot. For me, I'll be using my telephone as a scientific calculator. You may actually have a scientific calculator. It goes into scientific notation. We'll be dealing with that a lot. So that's not a bad one to look at. That's from page 696 until 703 or something like that. The appendix before that, Appendix C, is basically your periodic table. A great thing for chemistry type purposes. Not just that, it's also all kinds of measurements, and that's what I was getting at. Appendix C is your table, okay? And when you're beginning on page 686, you have tables for U.S. weights and measures, conversion table for length, and that's going from centimeters to inches, inches to miles, those kind of things. That's length. Conversion table for area is also table on page 686, table 3. Okay. Table 4 is on 687, conversion table for volume. Table 5, also on 687, conversion table for mass. Table 6 on that same page, conversion table for density. Then 7 is time on the next page, speed, and then finally you see table 9 on page 688, and that gives you the conversion between newtons and pounds and ounces, okay? And you were absolutely right. 1 pound is 4.45 newtons. Is that what you said? Excellent. Way to go, okay? You can find these tables that may have those for you, so you don't have to memorize them. But it's good that you have it. Going the other way, a newton is between 1/5 and 1/4 of a pound, 0.225 pounds. So a pound. Now, I do not know that answer. Are the pages even listed on the online books, ebooks? Some ebooks don't even have page numbers, which makes me irritated about ebooks. But okay. 688. What does it say? Table 7? That is it. Okay. Surely. Oh, that we're on page 127. Chapter 5, page 127 is where we are now. We started at 126 with example 1. Example 3 is on page 127. 2 and 3 are on 127. Okay. And that was the $50 or $60 one? Okay, not bad. Not bad at all. I bet you this book new is probably 200 plus. Probably used at the bookstore. I'm guessing maybe half that, or 4/10 or something. It's still pretty high. So that's great that you can find. And you said it took about 2 days to get it? Oh, with Prime. Okay. He's up there, isn't he? Okay. My wife has Prime too. Okay. Okay. Applied Physics, 11th edition, by Ewan Schroeder and Gunderson. It's a Pearson book, P-E-A-R-S-O-N, sideways. Okay, and I think the copyright date was something around 2019, 2017. So there may be another one coming out sometime soon, but you won't need it. This is the one we're using. Okay, do you need the ISBN? If you got it, I'll hold it up here. I don't know if you can read it. It looks like a 0-13-41. Is that a 5? You do. 80? Okay, well again, it could be the bookseller that they're going through. Maybe there's been a run on them since they heard we were using them, you know. Okay, I don't know. Okay. Right. Okay. Right. Okay, let me do that one. The mass is 1,000 kilograms, right? Oh, here comes Christavia. She's already been here. Okay. And you said the acceleration, you said was what, 2.1? 2.0 meters per second squared. Is that what you said? Okay. Now, this brings up another interesting point. I was going to get to it when the book got to it. You got to me earlier. That's why I wanted to show it now. If that doesn't say, if they do not put, you see the decimal is over here. Any zero following a decimal, if it's the last at the end of a decimal number, that's significant. Okay? These zeros up here are uncertain. If they don't have a bar or something like that over them to indicate they're significant, you would assume this is only one significant digit, just the one. If there was a bar over that one, that would be 2 significant digits. If the bar was over this one, that would be 4 significant digits. Okay? So where do you want to put the bar? No bar? One over this one, that one, or that one? It was your question, your problem, you choose. Doesn't matter. Oh, I thought he was just thinking really hard. No, okay. Yeah. I've known people like that. It's just for 1. And if you were to do that, then it would be 2 newtons. No 0.0. If that's the only significant digit here, 2 here, you go with the fewest number, 1. 1 significant digit, which would be 2. I'm sorry, 2,000, sorry. But those zeros are also not significant, but 2,000 newtons, okay? That was really poor. Okay, let me erase that and write it better. Okay. You multiply the 1,000 by 2, which gives you 2,000. Okay. But don't put any bars over anything. And that would be newtons, with only the 2 being significant. Okay? All right. Now here's the really weird thing. If that same problem, this would have been a 2.1 here, but this was only 1,000 here, it'd still be 2,000 because you only have 1 significant digit, that 0.1. Even though it's significant here, it can't be significant down here because there's only 1 significant digit. So weird thing about significant digits. And guess what? If I were going to be your teacher and continue with this, I usually don't count off for failing to do that. I usually mark them correctly so you'll know, but I don't usually count off. Okay? but we'll have to see what Dr. McMoule thinks of that. And this next problem, example 3, combines several new things, okay? So any other questions? Great questions, by the way, folks. These are exactly the kind of questions that get out right at the beginning of a term. Because I've had other classes just sit there really quiet, and they've been small classes too. They'll sit there really quiet, and then when it's time for a test or something like that, or doing problems, I don't understand these significant digits. And maybe you don't, so please ask, okay? And we'll try to focus on it. All right, any others before I clear it? All right, let's clear the, was there one? Okay, clear the drawing. Example 3, find the acceleration. Oh my goodness, this time acceleration's the unknown, okay? Produced by force, and this force is 500 newtons. Now notice how they wrote that, 500, and he put a bar over the second 0 newtons. That indicates how many significant digits? 3, exactly. The 5 is always 1, and the one with the bar is 1, and any in between that is going to be significant. So that's 3 significant digits. Applied to a mass of, so the mass is 20.0 kilograms. And by the way, folks, if you haven't noticed this, I'm going back and picking up things because you noticed we're starting in chapter 5, okay? Chapters 1 through 4 had really good information in them, but we didn't have time in this short course. It only meets 2 hours a week for only 16 weeks. You couldn't do all those chapters, so I'm trying to fill in the gaps for everything those did, including significant digits, okay? Now, what formula relates acceleration, force, and mass? Same one we've been using. Exactly. Now, you have 2 ways you can approach this. I can't remember if I talked about this before. I usually do. I call it either plug and chug or chug and plug. I don't care which, okay? The book usually likes to chug and plug. In other words, we're looking for the acceleration, so they usually start off by solving for the thing we're looking for. Well, how do you solve for that? Divide both sides by mass. And that will wipe out mass here, and that gives you acceleration is equal to force divided by mass. Well, now that's your chug part. Here's the plug part. Plug it in, plug it in. Okay, just like Glade. That's 500 with that second 0 being significant. Now, rather than newtons, I want to write the fundamental units. Anyone remember what a newton is? Kilogram meter per second squared. Perfect. Y'all are good. And you're dividing by 20.0. Now, notice any 0 at the end of a decimal number is significant. So you didn't have to put a bar over it. You know that's significant. 3 here, 3 there, okay? And this was kilograms. Now you might see why I wrote it in fundamental units, so we can cancel out the kilograms, okay? Now, that gives us 20 into 500. Well, you can do that on a calculator if you want to. I'm going to do it this way. I'm going to move that decimal 1 place to the left. I'll move this decimal 1 place to the left. And that makes it 50 divided by 2, which is 25. But we need 3 significant digits. So 25.0. What's left? Meters per second squared, which is a great unit for acceleration. Right? Does that make sense? Okay, and again, you didn't have to move decimals. You could just use a calculator, but I'm really lazy. I'm too lazy to use a calculator, so and they're so slow, okay? So I'm just kidding. All right, that is how you do any. Notice we could have had a problem to ask for what mass would you be dealing with if you had a force of this and acceleration of that? Then you would have solved for mass, and mass would have been force divided by acceleration. But again, use your fundamental units so you can cancel things out and see what you get. We have now finished, ding ding, section 5.2. Now again, if you notice when I was talking about the answers in the back, the odd number exercises have the answers in the back. So I would do sum of the odds 1 through 7. Okay. I would do sum of the odds 9 through 15. And then I would do sum of the odds 17 through 33. Now, if any of you think it's going to be a while before you get your book, I wish there was some way I could get these problems to you. What's that? Okay. Any of the odds 1 through 7, they're on page 127. Any of the odds 9 through 15, they're on 128. And then any of the odds 17 through 33, they're also on 128. Okay. Now, if y'all think most of you will have a book before next Wednesday, then I would say just wait till you get your book and then work on these exercises. If any of you are afraid you may not have one by then, if you want them now, what I might be able to do is go downstairs to my wife's iPad and do a, what do they call that? Adobe scan, and take pictures of this and put it out there under course material or something. Same place where the PowerPoints will be under week 2. Do any of you need me to do that, or you think you'll have a book in time? You want me to do it? Okay, I'll be glad to do that. I can't say that Dr. McBool would be doing this in the future. I don't know if he has a iPad with Adobe Scan in it, so I'll try to do that sometime late tonight or tomorrow. I don't know which. I can just tell my wife's downstairs. I can smell supper down there, and it smells so good. So I'm going to go down and eat before I do it. I promise you that. Okay, let's move on. Any questions before we move on to 5.3? Okay, now 5.2, by the way, was talking about, let me go back and give it, force and the law of acceleration. In other words, Newton's second law, F equal ma. F equal ma. What does that mean? The total force acting on a mass, m, that produces an acceleration a is that mass times the acceleration. Total force. Okay? 5.3 is talking about gravity and weight. Now, I think I will go to a new slide here. So any questions before I erase this one? Okay. And this time I think I'll type in again, even though my typing is really slow and bad. Let me type in a definition for you. The word is weight. The weight of an object is the amount of the, well, they don't put the in there, gravitational pull exerted on an object by the earth. Some books always capitalize earth. I don't, this one doesn't, so I won't do it here. That is the definition of weight. Now, when you step on the scales and you see the scale turn, mine turns way too much, whatever it lands on, that's your weight. And what is a weight? It's a pull. Pull is a force. That's why we use pounds to measure weight in the U.S. customary system. What would they use in the SI system? Newtons, absolutely. You could have said kilograms. That was a measure of mass. Weight is a force, so therefore you use either pounds or newtons. Sure, in the grocery store, when you see the scales that you measure your onions on or whatever, they'll say kilograms and pounds. Well, they're relating mass to weight. Those are different things. Weight is a force, and you use kilogram or pounds. Okay? Now, what formula does that for you? Now I'm going to go back to my, I'll go back to my pen here. And here's the formula that does it. Okay? Now, if this looks a little familiar, I can't write on my book, I need my pad. If this looks a little familiar, it should. F sub W. Okay? F by itself means total force. Sometimes books call it net force. This is force due to weight. So this means weight. Force due to weight is the mass of the object times, guess what it has to be? An acceleration, but it's a very special acceleration. That acceleration is given the symbol g. And that means the acceleration due to gravity. Okay? Now, in the SI units, G is equal to, let me use the same one the book does. Yeah. They use 9.80. Guess what units they would use in the SI system? Meters per second square, where G in the US customary system would be and is 32.2 what units? Feet per second squared. And by the way, if you want to just catch it, that means that 32.2 feet has to be the same length as 9.80 meters, because everything else is the same. Gravity's the same, per second square is the same, so this is a conversion between meters and feet too, but it's not a very handy one, but it is one. So that is G. That is the acceleration due to gravity. Okay? Weight is not 9.80. Yeah, that's 9.80. This is 32.2 feet per second squared. She's making fun of my writing. It doesn't hurt too much, you know, but I'll live through it. Okay. No, that's fine. My writing stinks, okay, especially with these ionizing pens. Okay, so weight is equal to mass times acceleration due to gravity. That is the weight due to the gravitational pull exerted by the Earth. Now, of course, if you were on the moon, you use a different G, because the moon is a different object. But not many of us will probably ever be on the moon. I know I won't, okay? Nor Jupiter or Mars or Venus or anywhere else. I'm going to live my whole life here on Earth, okay? So the acceleration due to gravity is a constant here on Earth. Not a constant anywhere else. I mean, not the same constant anywhere else, but here on Earth it's always the same. If you're at the bottom of the Dead Sea Valley or on the top of Mount Everest, it's very close to these numbers right there. Acceleration due to gravity, okay? And that's why, this is why, because G is a constant, that they can relate kilograms on your onion scale at the grocery store to pounds on that same scale, because they only differ by a constant. And that constant will be, it's not this constant, but it is just a constant. Okay. You have other things involved because they're different units. So here, we'll do example 1 in section 5.3. Find the weight. Well, remember, this book uses F sub W. A lot of books just use little w. This book uses F sub W. Find the weight, that's for the unknown here, of 5.00 kilograms. Well, what's that a measure of? Mass. 5.00 kilograms. Okay, have they given us enough information to get the weight? Sure they have, because here's the constant up here. So F sub W is equal to mass, that's all you need, times this constant up here, the one in the SI units, okay? And that would be 5.00 kilograms times 9.80 meters per second squared, and that would be something around 49, right? 0.0, I think it is. What unit? Anybody? Newton. Excellent. Y'all are good at this. Okay. Why 49.0? Because this has 3 significant digits. That has 3 significant digits. Your answer needs to have 3 significant digits. Done on a calculator, that would just come out 49. You have to put the 0.0 in there to make 3 significant digits. How did the book do? Look at that. They got it right. I'm so proud of them. Okay. Any questions? This is not a net force. This is not Newton's second law. But it looks just like Newton's second law, and sure it should. Because this is a force on this side, a mass over here, it has to be an acceleration here. Whereas before, the acceleration was whatever the acceleration of the body was. This one is the acceleration due to gravity pulling downward. Okay? I think I gave the illustration last time of an airplane traveling at 500 miles per hour in level flight, and we talked about what the net force was. 0, because it's not accelerating. Does that mean there's no acceleration on it? No. Gravity is pulling downward. That's not a net force. That's one of the component forces. Okay? Because the lift of the wings are pushing upward. So therefore, they balance out and you get 0 net force. So the weight is always there. If an object has mass, and every object has mass, it's got weight. Okay? Whether the net force is 0 or whatever it is. All right, ready for example 2? Any questions on this one before I clear it? Okay, example 2. Find the weight. So again, we're looking for F sub W. I'm so used to writing just W. F sub W, that's the unknown here. Find the weight of 12 slugs. That's 12.0 slugs. This is the only place you'll ever be using slugs. I promise you. Okay? What is that a measure of? Mass in the U.S. customary system, though nobody ever uses it. Okay? What is that weight? F sub W is equal to your mass times the acceleration due to gravity. Weight is the force due to gravity, so you have the acceleration due to gravity. Okay, this will be 12.0 slugs times acceleration due to gravity in the U.S. system. Anyone remember? 32.2 feet per second squared. Okay, this time I will need a calculator. Now maybe some of you already have done it. I'm kind of slow, old and slow. All right. Now, on your calculator, you don't have to put 0.0. 12 will do fine, times 32.2. You do need to put that one in there, like that, equal, and guess what you get? Is that what y'all got? Okay. What is the answer, though? That's it. You can only use 3 significant digits because this had 3, that has 3. So you take your first 3 digits, 3, 8, 6, and there happens to be a decimal. Okay. Look to the right. There is another digit there, but it's a 4. If that had been a 6, then that 6 here would have become a 7. You always round up if the next digit is 5 or more, and you just drop the digit if it's 4 or less. So this is what 4. So the answer is 386. What unit? Pounds. You got it. If you wanted to write slug foot per second squared, why would you want to write all that? Just put pounds. LB is much quicker. Any questions? Sure. Because in the U.S. customary system, well, there's 2 reasons, okay? 1, a slug foot per second squared is a pound, okay? And the other is the unit of force in the U.S. customary system is a pound. So both of those reasons pan out to be pounds. Now that may not be a very good answer, but does that make sense? A slug, yeah, a mass times an acceleration is a force. The mass in the U.S. customary is slugs. The acceleration in U.S. customary is feet per second squared. When you multiply those together, you get pounds. So that's what we got. After a while, using them often enough, you kind of get used to them. I never get used to slugs, though. Okay, it's so weird. Okay. All right. That was example 2, bottom of page 129. Let's go to 130. All right, this is where our next slide comes into play. Okay. All right. Come on. There we go. Poor old guy's still pushing on that crate. Okay, he must be tired by now. Okay. Here we have a brick sitting on a tabletop. Now we know that that brick has weight. Have you ever picked up a brick that didn't weigh something? No. Okay. So it has weight. The gravity is pulling down on that brick in this direction. Now, here's another timeout here. Quite often in real life illustrations like this, they'll represent the total mass as being located at one point. Okay? That's sometimes called the center of gravity. You don't need to know that, but it's how they usually do this. And we call that, goodness, it's there's a name for it, something another diagram, a point mass diagram, I think is what they call it, point mass diagram. You just put a point in there and just assume all the mass is right there, and this would be the weight at that point. Well, gravity's pulling down on that brick. You know it is. It has weight. But the brick's not accelerating. So that tells you the table must be pushing up on the brick with an equal but opposite force. And that force of the table on the brick is called the normal force. So this is F sub little w is the weight this way. If the brick is not accelerating, the net force is 0. That means it has to have a force pushing up on it equal to the opposite in direction to that force, and that is your normal force. Okay? Now, why do they call it normal force? Well, here's the surface of the table. And normal here doesn't mean as opposed to abnormal. It means perpendicular. In vectors, in physics, in geometry, normal means perpendicular to. And that's what it is. Perpendicular to the tabletop. That's the force pushing upward on the brick. Okay? So that's what that is. So Do you want me to type this one in, or do you think you can remember? That force called the normal force, this one right here, I'll go on and write it in. I won't type it. Okay, this normal force, why it's red, I don't know. But the normal force, F sub n, is, and that's what equal means, is perpendicular. Now I'm going to abbreviate that. That's my symbol for perpendicular to the contact surface. So the normal force is always perpendicular to the contact surface. Here's the contact surface, the normal force is exactly perpendicular, right angles to that. All right, make sense? Now, something I addressed earlier, they're getting around to now on page 130, and this is mass versus weight. Notice that the mass of an object remains the same. The weight varies according to the gravitational pull. Okay, well, we got that, remember? Force due to weight is mass times the acceleration due to gravity. Now, this is something you probably don't realize now, but I'm going to tell you. If you leave the surface of the Earth and go up into space, your acceleration due to gravity starts declining pretty quickly. Not super quickly, but by the square of the distance you are above the surface of the Earth. Or actually, more correctly, by the distance you are from the center of the Earth, because we treat the mass as if it was at the center. Okay? Just like we treated the mass of the brick at the center. So it falls off as you go up. And that's why the astronauts, you see them up there and they look like they're just floating around. We call it weightlessness. They're not really weightless because they still are close enough to the Earth, but they're just very, very low. Their weight has been reduced big time. But guess what? They have the same mass up there that they had on the surface of the Earth. So if any of you want a really quick weight loss plan, go into outer space, okay? And you lose weight. You don't lose any mass, but you'll lose weight. But the trouble is, as soon as you come back on the surface of the Earth, you get back at that same weight again. So, not recommended, but it was a dumb joke. It wasn't very funny. Okay, so here's what we mean by that. Force is mass times acceleration. So what if you had an astronaut of mass 75 kilograms? 75.0 kilograms. That's his mass, or her mass, it could be. And that astronaut is on the surface of the Earth. Then the weight of that astronaut would be that times 9.80 meters per second squared. And pull out your handy dandy calculator again. And what do you have? $75 times 9.8. And again, you don't have to type in the 0.0, equal 735. Is that what y'all got? 735 what? Newtons. Kilogram meter per second squared is a Newton. Okay? Now, what if that astronaut takes off, goes up into outer space, okay, and say is on the surface of the moon, say. This is one of the Apollo astronauts, actually walks around on the moon. The moon has an acceleration less than the, has a less acceleration due to gravity than that on Earth, because the moon is much less massive than the Earth, okay? And they'll go into that in chapter 11. We're not going to get to chapter 11. But anyway, you'll find out the astronaut weighs much less. And that's why when you saw them on the moon, if you watch those things, they sort of bounce around, you know, and they look like they're just having a big time up there. Even though they're in really heavy spacesuits and stuff, they don't have as much. So, let's clear this. We'll come back to it in just a minute because let's do example 3. All right, to go to white page. Any questions before I leave this one? Whiteboard. Okay, let me clear this. Any questions on that old thing? Okay. Find the 75.0 kilogram astronaut. That was a what? Measure of his mass. 75.0 kilograms. Kilograms measure mass. Weight on the moon, where G now on the moon is different from G on the Earth. It's a mere 1.63 meters per second square. That's considerably less than 9.80. Okay, so what will his weight on the moon be? The force due to weight, I'm going to put on the moon, is going to be the mass. Mass on the moon, the same as the mass on the Earth, times G on the moon, and that's going to be 75.0 kilograms. Same mass in both places, but the acceleration due to gravity on the moon, 1.63 meters per second squared. Now I'll get my handy dandy calculator again. 75 times 1.63. What you get? Okay, perfect. Ooh, goodness, that pen is doing whatever it wants to here. 122 newtons. I got 122.25, but you see that 0.25, not significant. Drop it, because that first two is less than 5. Okay, 122 newtons. What did they get? Look at that. What a weight loss plan. That astronaut weighed 735 newtons on the Earth, is now down to 122 newtons, but still has the same mass. Okay, so lost weight for sure, but didn't lose any mass. Okay, well, what good is that? Okay, any questions on that? Now they have another little blurb here that I don't really know why they do, and that's mass versus volume. And they say don't confuse these either. How do you confuse them? I don't know. There's just no, a volume is, and they give some of the units here. In the in the metric system, that could be cubic centimeters, cm cubed. Okay, these are volume things, SI. Okay, it could be, well, no, this is actually metric. Centimeter cube, that means so many centimeters long, so many centimeters wide, and so many centimeters high. Centimeter times centimeter times centimeter would be cubic centimeters. Okay, or it could be the in the U.S. customary, that could be cubic feet. Okay, another, let me just, rather SI, put metric. Metric. Another metric measure for volume, and this is especially if you're talking about fluids, liquids. Here's my water bottle. What is this? 1,000 milliliters, which means 1 liter. Because milli means a thousandth, this would be 1 liter. That water bottle right there is 1 liter. That's a measure of the volume of water, but usually that deals with fluids. That's the capacity of that bottle is 1 liter. Okay, so usually liter, and that they put little l. Most of the time we use a capital L. Any guesses why you might want to use a capital L rather than a little l? Especially if you're printing a little L, it looks like that, doesn't it? That would be easy to mistake to be a 1. So most of the time we use capital L. The bottle used a little L. I don't usually do that. So I don't see why you would have any confusion. They're just different things. Now what if you had two boxes that had exactly the same size? Okay, so let's say that this, I guess it's called a koozie or something like that, and let's say the bottom of that thing just going up to there, they have the same size approximately if you just cut it off right here. I'm not going to cut it off, but what if you did? Okay, but this would be much more massive than that because this is really lightweight material. So don't confuse them. Even though they might be identical boxes or whatever, if they aren't the same materials, they're not going to have the same mass. So mass is a function of how much of the object there is. And for some reason, I seem to have all my wires crossed here. I don't know how I did this. I've got my microphone wire wrapped around my leg somehow. I've just been moving around too much. Okay. So that finishes section 5.3. Okay. Now, if you get your books in time, the homework exercises here, I'd say do either 1 or 3 on page 131. Do either any of the odds 5 through 9 on page 131, and then do any of the odds 11 through 29, also on page 131. Any questions on 5.3? Yeah. Yeah, I'm going to do a Adobe scan of these two problem sets. There weren't any problems in 5.1. There are for 5.2. They happen to be on 2 pages, so that's going to be a 2-pager. And then 5.3 is all on 1 page. I will do all those and just put them out there as under week 2 instructional materials. I don't know, probably under etc. or somewhere there, I'll put those problem sets. Okay? Yeah, and oh, and by the way, now when you get Dr. McBool here, find out what he wants to do about homework. In my mind, homework is something that you do to learn the skills, to sharpen your skills. And do I want it turned in when I taught the course? Not necessarily, unless you're having problems with it. Now, the best way to, if you're having a problem, is either in class or even before class, email me or whatever and say, I don't understand how they got the answers. That's why I give you the odd numbers, because those answers are in the back. And if you can't get them, good thing to do, in my mind, is ask in class. Because if you ask in class, then everybody gets to see how to work it. Because if you're having that problem, the odds are at least half of the class would be having that problem as well. Okay? So don't ever hesitate. Always ask. And I'll be glad to work anything as long as I'm teaching, which won't be past next Wednesday. I may be teaching next Wednesday, but so if he wants you to turn in homework, then turn in the homework. But I don't require that unless you say, hey, I'm stuck here. You send it to me in an email. What am I doing wrong? I'll try to figure it out and send it back. But even that way, you can get somewhat immediate gratification. You don't have to wait a week. But if you want to wait till the next class, it's a good time to review and make sure you know how to do those problems. So be sure to ask any of those. If I'm the teacher, that's how I do it. You'll have to wait and see how he does. Okay. The next topic here is friction. And actually, I want to go back a little bit. Okay. I'm going back to our good old buddy here. Okay. Now it's going to go up to where we just were, but I want to go back to where we were before. There it is. He's pushing. Oh, you can tell he's really straining But guess what? He may not be moving it anywhere. Why? Even though he's got a push in that direction, notice the arrow underneath it is a line in that direction. What is that? The friction of the box, the crate, whatever that is, on that rough pavement, whatever that is, your driveway or whatever it is. That's friction. Notice a few things about friction. It always opposes the motion. If he's pushing that way, friction's pushing this way. If he's yanking on it this way, friction's going to be yanking on it the other way. It always opposes the motion. So let's go back to the whiteboard. Let me see. That's before we go to the whiteboard. Here is a front end loader, okay, pushing against a really big crate, okay. It's pushing this way, and whether it can move that crate or not, I don't know. Depends on how much oomph it has behind it. But as much as it's pushing this way, it looks like friction is opposing the motion. And if this line is the same length as that line, it's not moving. You may be spinning your wheels, you may be doing whatever if it's not moving. Okay, why does friction operate like that? Well, if you were to get on the microscopic scale and look at the difference between that surface there, say that pavement down there, and this crate or box here, you see on a microscopic scale the surface down here is not smooth. It's jagged. The box, the crate, is not smooth. It's jagged. Now let's just imagine that you scoot this back this way a little bit, so it's this point here is down in that groove, and this little point here is down in that groove. You try to move it, and now you're bumping against the edge of the grooves. That's friction. Now when it gets to the top of that and you push, then it may be easier to keep pushing, okay? And we'll talk about that in a minute too, but that's the nature of friction. The surfaces on a microscopic scale are not smooth. They interfere with each other. They fall down into the grooves of one another, okay? And that makes it hard to move. So I don't think it lets me type on this. I'll go on and write it on here, okay, if I can get my pad back. Okay, friction is a force. It is definitely a force, okay, that resists, yuck, I don't know if you can see that, yuck, there it disappears, okay. I don't know, did y'all see anything there, or you, okay, it got on my screen and wouldn't go away, okay, that resists the relative motion of two objects in contact, have to be in contact, caused by irregularities of the two surfaces sliding or rolling across each other. I'm abbreviating some because I'm running out of room. Okay. And that's exactly what we are observing here. That's what it is. It's a resist the relative motion of the two objects in contact with each other caused by those irregularities of the two surfaces, either sliding or rolling across each other. Now, notice that sliding friction is generally always much greater than rolling friction. Actually, these tires rolling on the surface, that's what enables it to push, okay? The box here, crate, whatever it is on the surface, that doesn't want to be moved, okay? But we're not really going to deal much with rolling versus sliding. What we will talk about is static friction, that is stationary friction, as opposed to moving friction, which is used the term kinetic friction. We'll talk about that a little bit later. Okay. Now, if you can imagine, right sitting next to me here is a bed. Okay. Now, I've lost my time here, 4 minutes. Okay. If I were to push on this bed, more than likely I'm not going to get it to move, because the friction of the feet of those bed on the floor. Let me back off one second here. Notice here, this surface here. What if this is a pretty light box? Then it wouldn't take much force to make it move. But what if I then put weights on top of the box? That forces these down into the grooves even deeper, and it makes it harder to do. So sure enough, friction depends on, and what do we call that? The forces? The normal force. The forces that are above, perpendicular to the surface. Friction is proportional to the normal force. Okay. I'll get that out there. We'll run into it later. Okay. So why did I bring that up? I guess just the illustration of this at the moment. Okay. Now, what if one of those surfaces, that bottom surface especially, was very slick ice? Okay? Hey, it's not going to have very much friction at all. And that's why then who would be at a disadvantage would be this wheel here. If that was really slick ice, the wheel couldn't even push on it, because there would be very little friction between the tire and the surface. However, if you came over, and especially if you had spiked shoes on or something like that, and pushed on it, you might be able to push this where this thing wouldn't be able to push it, because it wouldn't get any friction between its tire and the wheel, the wheel and the surface. So that was sort of a dumb example. Let's move on from there. All right. We're not quite there yet. Let me, and this is what I was talking about before. If I push just a little bit on that big old heavy crate, or this bed, just push a little bit, okay? The bed pushes back at me with just a little bit, because the net force is 0. If I push even harder, it pushes back harder, because it's not moving, the net force is 0. But if I do manage to push hard enough to make the bed move, now the bed is no longer stationary, static, it's now moving. You've gone to a new type of friction, that's kinetic friction. So let me write down at least the beginning of the difference there. Static friction is the force my writing is terrible, that opposes the start of relative motion. Notice here, the start of relative motion. Remember, it's always relative motion. Of two objects in contact with each other. I'm abbreviating like crazy. Okay. Now that is when these, where are they? Come on, where are you, pen? When these valleys here are down in those valleys here, and it's really hard to get it to move. You're pushing, but they're going, this side is pushing against that side. It's hard to move. Then that's static friction. When they're down in the grooves and you can't get it to move. When you finally hit enough force to get them to move, you get them up on top of the peaks to peak. And now it's easier to move because they're not down in the valley. Well, then you have moving friction, and that's kinetic friction. Once the touching objects, and I'm running out of time, I bet. Am I? Yeah, we've already passed time. Let me just read this one more. Once the touching objects are in relative motion to each other, the friction is generally less and is called kinetic friction. Kinetic means moving. Kinesiology is the science of motion. Okay? Kinetic energy is the energy of motion. The word kinetic means you are actually moving. Static friction means stationary, static, stationary, not moving. That's usually not a lot greater, but a little bit greater than static friction, than kinetic friction. And you've probably experienced this before. If you've ever been pushing on something and pushing on something, it's really hard, and then when it starts moving, you almost fall down because the kinetic friction is usually less than the static friction. Okay? And we'll begin next time, whoever the we is. It may be me, it may be y'all, okay, and Dr. McBool. But we'll begin with these three, or let's see how many statements. Yeah, 3 statements on friction. They're on page 132 and enumerated 1, 2, and 3. Okay? And then we will pick up, or y'all will pick up and go from there. Okay. Any questions? All right. Yes. Okay. What an excellent question. Okay. Now, I'm going to start with a little dumb story. When I was a young kid, I don't remember what age it was before we had our first air-conditioned car. It was, I think I was, probably out of college or something. Our family was cheap. We were not that wealthy, so we were pretty cheap. So we always, the air conditioning is called 460, okay? Roll down the 4 windows and drive 60 miles an hour. And that's what we had to do for air conditioning. And I love to, if we were driving along, stick my hand out the window and feel the wind pull my arm back. Why? Because air has friction in it, okay? It wouldn't have yanked my arm back except that air has friction, okay? Same thing with water. If you've ever swum, you push against the water because the water has friction. It's not nearly as much as gravel or a concrete driveway or something like that, but yes, it does have friction. A speedboat going through the water, you can hear it rubbing the thing going as it bangs along on the top of the water. Water does have friction. Not nearly as much friction as a solid surface, but it does have friction. That's a great question, and yes, it does. And even air has friction. Okay? That's what creates, move your hand like that real quickly. You can feel the air molecules hitting your hand. Okay? You don't feel them individually, but you can feel something is touching your hand. Even air has friction. A vacuum has no friction at all. Okay. Was that answering what you were asking? All right, good deal. Any others? Great questions, by the way. All right. Well, this may or may not be the last time I see you. You have been a great class, and I kind of would look forward to meeting with you next week, but maybe Dr. McBool will be here by then. So I'll pass along where we are and what we've been doing and let him decide how to go from here. All right, good deal, folks. I'm going to stop sharing. I'm sick and tired of sharing, so I'm going to stop my sharing here. All right. If there's no other questions or other issues, I will end the recording for everybody. And some people are already leaving, so take care, folks. Have a great term if I don't see you again. Bye-bye. Bye-bye.